Hello, everyone. My name is John Lin, and today I'll be giving a quick overview on the topic program partitioning and dialog analysis for MPI based on logical clocks. And this is from the paper by Li Sushan et al., published in Parallel Computing. So for our background, from class, we learned about high performance computing clusters. It's a technology that leverages clusters of powerful nodes to run multiple jobs simultaneously on numerous computer servers or processors. We know that the cluster relies a lot on the message passing interface or MPI. And MPI is widely used just because of this portability, efficiency, and the process level communication. However, the problem of MPI is that MPI is susceptible to deadlock errors due to its nature of non-determinism and asynchrony. So to just give more background on MPI and deadlock, there are two types of communication mechanisms in MPI, which are blocking and non-blocking. So for blocking, we have APIs like send, receive, barrier, wait. For non-blocking, we have something like I send and I receive. From different combinations of blocking communication APIs, we can get two types of deadlocks, the deterministic deadlock and potential deadlock. So the deterministic deadlock is when it is caused by direct circular weights during program execution, and it can be detected with a single execution of the MPI program. On the other hand, the potential deadlock arises when you use wildcards receives. So that would be when you use like MPI any source with the receives. So this brings a non-deterministic behavior because the deadlock may or may not happen on the runtime. And from this behavior, it makes it very difficult to debug and or detect potential deadlocks. So there have been some solutions to do the deadlock detection in the MPI programs. So the traditional deadlock detection um, is where you basically explore all execution paths. However, this solution is not feasible because of the problem of path explosion. So path explosion refers to the rapid growth in the number of possible execution paths in a program. So as the number of processes and communication events increases, the number of possible interleavings basically grow exponentially, making the deadlock detection very slow, inefficient, and infeasible. So as you can see, the path explosion basically makes the deadlock detection very challenging to do it efficiently. So ISP is a solution where it's like a tool to detect API deadlock. I mean, detect MPI deadlock by exploring different execution paths using partial order reduction. So partial order reduction is just an algorithm that allows ISP to avoid analyzing all interleavings by reducing them to only those that are meaningfully different. So um, it was like a way to alleviate the path explosion. However, ISP still struggles with path explosion, especially in complex or highly concurrent MPI programs. So there is another solution, which is SAMPI, and it detects potential deadlocks in MPI programs by using symbolic execution. So instead of running the program with concrete inputs, it basically explores all possible communication paths using symbolic values and builds a state space of feasible executions. It then uses SMT solvers to check whether a sequence of sends and receives can lead to a deadlock based on NPI's matching semantics. And this method allows SAMPI to catch bugs before runtime, but SAMPI still suffers from path explosion as the number of branches and processes increases, similar to ISP. And there are solutions like NPISV, NPISE, and TASS, but these all face the problem of path explosion. So, um, in order to alleviate the path explosion problem better, the authors of the paper came up with the program partitioning approach. So this approach for now only considers single path MPI programs where values of messages do not affect the schedules of a program. So to give a quick overview of the approach, it first partitions um, the program into smaller components based on communication matchings to isolate the analysis. It then assigns logical clocks to track when each communication event starts and completes. Finally, it detects deadlocks by exploring possible matchings only within each partition, which reduces the path explosion problem. So, to go more in depth of the approach, we'll start by looking at the first step, which is to create the matching relationship graph. So, in order to create the matching relationship graph, we use the LLCP algorithm and the matching detection rule to create it. So, the LLCP algorithm or the lazy Lamport clock protocol algorithm is where you assign logical clock values to all events, where the clock values represent when the events are issued or returned. And the matching detection rule tells us that send and receive match if their parameters match, and the send's clock value is less than the receives clock value. Also, two barrier events also match if they share the clock value. So, from the LSTP algorithm and the matching detection rule, we get the matching relationship graph shown on the right, where the vertices represent the communication events and edges represent the valid matchings by the matching rule. So, um, so with the matching relationship graph, we move on to making the preliminary partitions. So basically, from the matching relationship graph, we identify connected components, and each connected component would basically represent a partition, and each partition would have events that might match or influence each other, and the events within each partition would not really and with the preliminary partitions, we will later on use the dependency relationship graph and create a final partition to do the deadlock detection. So, uh, in order to build the dependency um, relationship graph, we first need to talk about the completed before relationship. So, um, in order to figure out the completed before relationship, we use the BLC algorithm, which we use to understand the order of events within each process. And so in the algorithm, each communication event is assigned two logical timestamps, C return of E, which represents the time is returned to the process, and C complete of E, which represents the time by which the communication event must complete. We then define a complete before relationship for two events, E and E naught, in the same process. And we say E completes before E naught if either C complete of E is less than C return of E naught, or they have the same C complete but E returns earlier. And we basically would want to have the relationship for every event in each process. And the pseudocode on the right basically shows the BLC algorithm. So now we understand the before relationship. So we want to extend completed before relationships to the partitions, the preliminary partition we built before, and we create the final partition. So before building the dependency relationship graph, we want to first talk about the clock range representation, which is shown on the right side of the slide. So for all processes in a partition, we basically want to find the SC start, which is the latest issued or return time for any event in partition K from process P of I, and we want to find the SCN, which is the earliest completed time for any event in partition K from process P of I. So, for example, for process zero for example, shown on the right side for process zero and partition zero, um, it would have the SC start value of 1 and SCN value of 3. So once we have all the clock range representation for all processes in all partitions, so we want to basically for every pair of partitions P, partition I, and partition J, um, if there exists a process such that the SC end in partition I is less than SC start in partition J, we add a directed edge from partition I to partition J. And this just means that partition I must compete before partition J begins on process K. So we basically do this for every pair of partitions, and we would end up with a um, dependency relation graph with a lot of edges. So we then use the Tarjan's algorithm to find strongly connected components and basically merge them into single strongly connected component and basically have a final partition in order to be used for the the deadlock detection. So we basically from the preliminary partition, we basically add the edges from looking at the dependency relationship, and then after using Target's algorithm, we would have a final partition that we could use to do the deadlock detection. So at this point, all interacting events should be grouped together in a partition where um, the elements in each partition don't really affect um, the other partitions. So for each final partition, we can explore all possible execution paths, and we can detect if there's a deadlock, if there's no feasible match for a receive, especially the wildcard receives, or if all processes in the partition are blocked. And since all partitions are basically independent, the search space is much smaller. Since each search is basically local to each partition, which makes them very scalable and very efficient compared to the previous solutions that we talked about. So the authors in the paper basically did some performance comparison against ISP and SAMPI. So the PDMPI here, it represents their approach, the partitioning approach, and they did it with some test suite. Um, so they ran the performance using Intel Core i7 8700 processor running at up to 3.2 gigahertz and 8 gigabyte of DRAM. And PDMPI was able to outperform ISP, and it was also it was it also had a similar performance with SAMPI. Um, they also did some performance comparison with real world open source programs. So here PDMPI outperformed ISP again, and we see that when the communication structure of the program is not like highly dependent, PDMPI outperforms SAMPI. So to summarize, um, basically this approach, the partitioning approach, basically uses a combination of um, matching relationship graph, um, dependency relationship graph, in order to build up to a final partition, in order to detect deadlock in a MPI program. Using the final partition basically allows the users to reduce the number of execution path search, since the MPI programs would be broken down into multiple partitions. So basically, what this means is here we said the communication structure of the program is not highly dependent. This means that we would have a lot of partitions, meaning that the search space for each partition would be even smaller, which allows the PDMPI to outperform SAMPI. So the only downfall to this approach is that, like I said before, it is only suitable for single pass programs. So the next step for this approach would basically be to extend the approach to multiple path MPI programs by using symbolic execution. So this means that we would combine some elements from PDMPI and some elements from SAMPI in order to create a better solution that outperforms this PDMPI solution and um, allow the approach to be used in multiple path MPI programs. Thank you.